Hi everyone, so here's our moments challenge question from last lesson. So I'm just going to read through the question and I'm going to add to my diagram some different forces and different information that's given in this question. So the first thing to take from this is that it's non-uniform. So a non-uniform, you'll remember that means that the weight, 5G acting downwards, is definitely not in the centre of this. So that's the first thing that we've got to really keep our eye out for. So wherever I put my weight on here, I must make sure that it's not in the centre. Okay. 5 kilogram mass, length 4 metres, and it rests with one end A on rough horizontal ground. And again, that's going to be important because there's going to be some resistance to motion there horizontally. So it rests, and again, here's another word, it's just resting with one end at A here. And what that means, if it's just resting, we talked about this before, if it's hinged, then there's going, if it's fixed here, it's hinged, there's going to be components of forces acting parallel and perpendicular at that point. But if it's just resting on the ground, what that means is we've just got a reaction perpendicular to the ground caused by this thing just sort of sitting, just touching the ground there, just resting on the ground. So I'm going to put that on first of all. So I'm going to put a reaction force on, always acts perpendicular to the point of contact. So that's what's happening at that point. We've also got this rough horizontal ground, so that means there's going to be some frictional force here. And again, if we think about this, let's get our direction right. This was just resting on the floor. If this was smooth, if there was no resistance, no friction here, then this thing would tend to just slip that way. Okay, it would just go that way to the floor. So it's tending to go in this direction. So because it's rough, something's stopping that happening. So there must be some resistance acting against the way that this wants to move. So it wants to move that way. So the resistance must be in this direction. So I'm going to put a frictional force on there. And we will be doing some more work on friction later in this chapter. So I'm just going to put friction on there. I'm just going to call that FR for friction. Okay. So there's my forces acting at that point. The centre of mass of the rod is d metres from A, so we can put this d on here as well. And I don't know where that's going to be necessarily, but I know it's not in the middle. And again, we've seen this before. If I do put it accidentally in the wrong half here, then it will all work out when I work out d later on. It would all work out in the question anyway. So I'm just going to put somewhere on here where this distance is d. So if I need it, this bit's going to be 4 minus d, because the whole length is d. The whole length is 4. So my weight is acting down, and my weight is 5g in that vertical downwards direction. Okay. So this rod is being held in limiting equilibrium. And limiting equilibrium means it's, again, on this point of slipping at the floor here. It's got to the point the friction has built up and built up and built up, and this thing's about to go, but it's being held in equilibrium. So it's definitely in equilibrium here. Angle theta to the horizontal, and it's this force here that's holding all of this in equilibrium. Okay, and this is acting perpendicular. What are we asked to do? We're asked to find in terms of dg and theta, so one of those questions where there's not actually many numbers in this, the magnitude of the vertical component of the force exerted on the rod by the ground, so that's this RA, reaction at A, that's what that's asking us for, and also the magnitude of the frictional force acting at A as well, so that's going to be FR that we put on our diagram there. Okay, so I'm going to get another piece of paper now. I'm going to have a look at actually working through this question. Okay, so first of all, let's have a look at trying to get some of these things involved. And again, here we could take moments about any point at all that we like. That's up to us. We'll have a think about that in a minute. We can also have a look at vertically and at horizontally as well. Because this is in equilibrium, then the resultant forces in any direction must be 0, and the sum of our moments must be 0. So let's have a look at vertically first of all. So vertically, tell the examiner which way. I'm going to take up as positive. We've got RA acting upwards. I've got my weight, 5G, acting downwards. And I've also got part of this force acting upwards, not the whole force, but part of this force is definitely having an upward force here, upward component here, and it's also got a component horizontal. So I'm going to split that force up. Okay, so I'm going to split this force up into its vertical and its horizontal component. So the resultant of these two components would give me this diagonal force of that rectangle, if you like. Okay, so it would give me this resultant. Let's have a think about angles on that then. So if I look at this angle, if this is theta here, then this is going to be theta, alternate angles. If this is theta, then this is going to be theta as well. So I'm going to put my theta sort of within these forces here. I want it to be adjacent to my resultant force P. So let's just check that again. This angle here was theta. So this angle here must have been theta. And then this one will be 90 minus theta. And so this one will be theta as well, because that makes 90 degrees. So that's definitely theta there. And we've talked about this a little bit before, but again, our resultant force is always our hypotenuse here. So if I looked in this triangle, where this component would be this part of the vector here, then this is definitely my adjacent. So it's going to be, if I did cos theta, it would be cos theta equals this component over P. So this component here must be P cos theta. And then the other component must be P sine theta. And we can think about that as being part of this triangle here of vectors. So this vector here, same as this bit, and this bit here is definitely P sine theta, opposite and hypotenuse here. Okay, so P cos theta, P sine theta. And we've talked before, I think, just in a previous lesson, about the component adjacent to the angle always being cos theta, because adjacent over hypotenuse, that gives me cos theta. So P cos theta is that component, P sine theta is this component. Okay, let's get back to this. So vertically, up RA, down 5G, and now up, we've got our P cos theta as well. So if up is positive, that's plus P cos theta. And that, nothing's happening vertically, because the whole thing's being held in equilibrium. So that resultant force must be equal to 0. I'm just going to make RA the subject of that, because RA was the thing that we were trying to find. Okay, so there's one equation. I'm also now going to look horizontally then, because again, the whole thing's in equilibrium, so horizontally, the resultant force must be 0. I'm going to take right as positive. Let's tell the examiner that. So looking at this frictional force is acting in that positive right direction. No component of this, because this is just vertical. No component of this, because that's just vertical. But then here, this one, P, has got a horizontal component, P sine theta, and it's acting in our negative direction now. So friction, FR, frictional force, minus P sine theta is equal to 0. So my frictional force is going to be P sine theta. And looking at this now, I want to find out what RA is. The question asked me about RA, the question asked me about friction, but it didn't want P involved. Okay, it said we could have G and theta involved, but it wanted D, this distance, involved as well. So what I'm going to do now, I'm going to need to try and get another equation to try and find P, and then I can substitute in to answer this question. How am I going to do that? I'm going to take moments. I want P involved, so I'm not going to take moments about B. I could take moments about this point. I'm going to take moments about A though, because then my frictional force and my reaction force here at A, they're not, the moments of those at A are going to be 0. They're not going to have any turning effect because they're acting at A. So that's going to simplify things down. So I'm going to take moments about A. Tell the examiner I'm taking clockwise as positive. So clockwise, this 5G is going to be acting in a clockwise direction, so that's going to be positive. And then the action line of that force is down here. So my perpendicular distance of this force from A is definitely not D, because that's definitely not the perpendicular distance of the line of action of that force from A. It's going to be this distance here. Okay, and this distance here, if This is D. Think again, right angle triangle. This is going to be D cos theta. So 5G, and then my perpendicular distance there is D cos theta. And then the only other force I've got causing moments here is this P, which is tending to turn this thing anti-clockwise. So that's going to be minus P. And then the perpendicular distance of the line of action of that force from A is this full distance, 4 metres, and that's definitely a perpendicular distance there. So a little bit of rearranging. 4P equals 5 dg cos theta. So P is 5 dg cos theta over 4. And the question wants D and G and theta involved, so that's looking good now. All I'm going to do now is I'm going to say, right, substitute this in here for P to get a formula for RA, substitute this in for P here to get an expression for FR, and then that's my question completed. So I'm going to call this 1 and 2. And let's now say in 1, I'm just going to move that across slightly. So in 1, I'm going to put P in here. RA is equal to 5G minus all of this, P, times cos theta, so minus 5 dg cos squared theta over 4. I could leave it like that, or I could put it all over 4 if I wanted to. So RA, 20g minus 5 dg cos squared theta all over 4. So there's my answer for RA. And then what else do I want? I want friction. So I just need to, again, I'm going to substitute this in to that expression 2. So my frictional force is P times sine theta. So 5 dg cos theta sine theta over 4. And there's my 2 answers to this challenge question.